This is lecture number 11 of the course Engineering Mechanics. In the last lecture, we were considering the motion of this cylinder with respect to a frame F. Now the surface of this frame F or the rigid body F is curved as shown, and its local radius of curvature is capital R. The small cylinder that is rolling on this body F has its radius as small r. Our interest has been to find out the velocity and acceleration of a couple of points of interest. In the last class, we found that the velocity of point P1 with respect to F must be 0, since the smaller cylinder is rolling without slipping on body F. So no slipping gives us this relationship. In the last class, we also found that the velocity of point A with respect to F is omega small r et. Now point A is the center of the cylinder, the rolling cylinder, and omega is the angular velocity of this small cylinder with respect to frame F. Its direction is clockwise as perceived by the observer fixed in F. Et is of course the local tangent unit vector to the trajectory of point A at this shown instant, and this broken line is denoting the trajectory of point A as seen by this observer fixed in F. This is trajectory of A with respect to F. We also found that the acceleration of point A with respect to F turns out to have two components. One component is along ET and the other component is along En unit vector. This is what we derived in the last class, where omega dot is the angular velocity of the small cylinder as seen by our observer fixed in F. Now the next and the final item as far as this rolling without slipping scenario is concerned is to find acceleration of point P1 with respect to F. P1 is a point belonging to M and is currently in touch with the frame F. We want to find this quantity. Right? How do we find AP1F? To find AP1F, I am going to use the acceleration transfer relationship, ATR. However, before we can use ATR, we need to identify our intermediate frame and an intermediate point. These are required before we use the ATR. Now the IF that I am going to choose is body M, and IP I am going to use as point A, and A is indeed a point fixed in M, as it should be. IP should always be fixed in IF. Okay, so I'm going to use this space to find AP1F. AP1F is going to be written as this is the expression for AP1F using M as IF and point A as IP. P1F. It's good to verify the various indices here before we proceed further. Looks fine to me. As usual, having written the acceleration transfer relationship, I would like to sweep from right to left and mark the quantities which are known as K and mark the quantities which are unknown as U. And whenever I come across a new unknown quantity, I would like to write a new formulation so that I can find that unknown or can convert that unknown into a known quantity. I start with AP1M. I mark that as a known quantity. It is actually 0 because P1 is a point fixed in M. Go to the second term. This is 0. It's a known quantity. P1 is fixed in M. This is a known quantity. Omega MF. Indeed, we know omega MF. It is a given quantity. It is omega times K hat. where k hat is a unit vector pointing into the plane of the screen. So this is a known quantity. RP1A is going to be small r times En. Remember, En is the local normal unit vector to the trajectory of A, and right now at this instant it is pointing downwards. All these are known quantities. Omega dot mf. Is this a known quantity? Indeed it is. This is omega dot k hat unit vector. I mark this also as a known quantity. I come across AAF. Is this a known quantity? Yes, it is a known quantity. In the last class we derived AAF as this. I wrote on the previous slide also at the beginning of my lecture. Indeed it is a known quantity, and thus everything on the right hand side of this equation 1 is known, and thus we can find AP1F. If all these quantities are plugged into equation number 1, one will arrive at the following expression for AP1F. So AP1F has a single component along minus En, which means at this shown instant acceleration of P1 is pointed towards A, and it has magnitude as omega square small r big R product divided by R plus R. Okay. So in summary, what all we have found so far as for as far as the motion of this small cylinder on this big cylinder is concerned. We found this, rewriting all the expressions. This is all we have derived so far. This derivation was based on the understanding that the frame F is having this curved surface with radius of curvature as r. It is interesting to see how these four expressions simplify if we consider a case in which r is very large, a very large quantity. Take r to be almost equal to infinity. Now mind you, when r is equal to infinity, it implies that f has a flat surface. Then m is rolling without slipping on a flat surface. So this is a special case of the scenario we considered. Even though this is a special case, r equals infinity, it is quite a common case. We often find a cylinder or a circular body rolling without slipping on a flat surface. How do these expressions simplify? Of course, Vp1f will still be 0. There is no modification per se. However, AP1f will get modified. It will become simply minus omega square small r in En direction. So remember, this is point P1 belonging to M, and we had En pointing downwards, and this point is A. So AP1f will have no dependence on R, and it will be a finite value minus omega square R En. As far as VAF is concerned, there was no appearance of big R, so it just remains the same. It has no impact, it has no influence of the fact that the surface of F is now flat. However, AA1F will have some influence. Its component along ET remains unaffected, but the component along En is actually 0. It vanishes when r goes to infinity. So acceleration of point A just remains omega dot r times Et. And that makes perfect sense, because the surface, if the surface of F is flat, then the trajectory of A will not be curved anymore. The trajectory of A will be a straight line parallel to the flat surface, right? And we know that if a particle is moving along a straight line, it may or may not have acceleration in its tangential direction, may or may not have, but we are sure that it cannot have any acceleration in the normal direction. It cannot have any acceleration in the normal direction if the trajectory is a straight line. That's what is happening here. We do get a non-zero component of acceleration of A along ET, but the component along En vanishes. All these results that we have derived could be used readily in solving many problems of practical interest. These equations, these relationships will prove very handy in analyzing the motion of a rolling object on its surface. Moving on, the next topic of our interest is what we call as the instantaneous axis of rotation. Instantaneous axis of rotation of an RB, of a rigid body, with respect to another rigid body or frame. Instantaneous axis of rotation, and I will use this acronym IAR to refer to this otherwise long phrase, instantaneous axis of rotation. What do we mean by this, and how and why is it a useful quantity, a useful entity? To define IAR, let's consider a pair of RBs. As usual, I have frame F, frame M. Let's consider this line, straight line, as L. This straight line L will be called definition of IAR. L will be called the IAR of M with respect to F if VBF equals 0 for all B's which are part of this line L and B is part of the body also. This is the definition. So if L is the axis of rotation, all these points, this point B and all such B points on this line or axis will have VBF 0. The definition is quite simple. Suppose we are able to find this line L. Suppose we are able to identify the instantaneous axis of rotation of body M. How is it useful? Why do I bother? The utility of axis of rotation is that it may help us find the velocity of a particle, a point on M in a simple manner. Mind you, if P is a point fixed to M, VPF can always be written as using the velocity transfer relationship. This expression is anyway true whether B lies on L or not. So in general, velocity of any particle on the body can be found using B as intermediate point and of course M is the intermediate frame, and B is fixed to IP, fixed to IF. This is generally true, two terms. However, realize that if B lies on IAR, then it implies VBF is 0, and then you can find VPF using one term alone, just one term, that's all. Just one term. There lies the motivation of knowing or trying to find the axis of rotation. If you know the axis of rotation, you can choose any point B on that. You can use that as the intermediate point, and if you use that point as an intermediate point, velocity of any particle P on the body can be expressed simply as one term, omega mf cross rpp. Less algebra. Also easy to visualize the motion of the particle P and the rigid body also. So these are the two advantages. Less algebra, easy to visualize motion, visualization is easier. Thus we want to find the instantaneous axis of rotation. The next question is, does an instantaneous axis of rotation always exist for a body? Existence of IAR. If you are considering the motion of a body in non-planar mode, non-planar motion, motion of what? M with respect to F. If the motion of M with respect to F is non-planar, IAR may or may not exist. May or may not exist, not guaranteed. If it doesn't exist, we cannot find it, and the whole narrative about IAR has to be stopped. An example of a case in which the IAR may not exist is the following. Consider the motion of an aircraft. So this is the front view of an aircraft. Being observed by our observer F, ground frame. Now this aircraft is having a motion such that its center of mass of the aircraft is having some velocity v0 not equal to 0, and at the same time suppose it is having some angular velocity also not equal to 0. In this case we can show that instantaneous axis of rotation does not exist. I am not giving the full proof, the entire proof here. However, it can be shown that IAR will not exist. So non-planar motion, no guarantee. In contrast, if the motion of m with respect to f is indeed planar, IAR does exist. Guarantee that it will exist. That also can be proved. However, in this lecture I am not showing that proof. Now, if the IAR does exist, how do we identify? How do we identify IAR? There are two ways. One is more mathematical, where you will have to solve a linear set of equations. This course we are not going there. The other is by visual inspection itself. You can find IAR in the case of planar motion. Here also, if it exists, the option of finding by the mathematical way of finding is still there. Okay. Even visual, some cases visual inspection can also give you that. But this course we will not worry about IAR in as far as non-planar motion is concerned. We will only focus on planar motion, and for such planar motion only visual inspection. I will show 3 cases in which a visual inspection can help us identify IAR. However, before I show those cases of visual inspection, I have one more quantity to be defined, and that quantity is similar sounding instantaneous center of rotation. ICR, we will use the acronym ICR, of a body with respect to a frame F. And we will discuss instantaneous center of rotation only in context of planar motion. So suppose we have a reference frame F and E1, E2, E3, what I have drawn on the screen, they are fixed in F and then there is a body which is having planar motion with respect to frame F. Now, since this body is having planar motion with respect to F, it implies that its omega mf must be parallel to the E3 axis without loss of any generality. I mean, for having planar motion, it can be tilted also. I mean, its omega mf can be tilted also with respect to E3, but then I can always argue that I would reorient my E1, E2, E3 which are fixed to F in such a way that whatever is the direction of omega mf, that lies parallel to, that is parallel to E3. Now, for such a planar motion, if we consider a plane perpendicular to a plane which is perpendicular to the direction of E3. So suppose we consider a plane like this. Okay. We consider a plane like this. And then suppose we know somehow what is the instantaneous axis of rotation. Suppose this is the instantaneous axis of rotation, and it will turn out to be, for such a planar motion, the instantaneous axis of rotation will be parallel to omega mf. It has to be. It will exist and it will be parallel to omega mf. Now, the point where the IAR intersects with this plane, let's call this plane as P. Let's call this plane as P. This point of intersection of IAR and plane P we will call as the instantaneous center of rotation of M with respect to F in the plane P. In the plane P. Okay. Point of intersection of IAR with plane P. Now, if you consider another plane here, say P prime, the IAR will intersect that plane here at this point, and that will also be an instantaneous center of rotation of body M with respect to F, but in the plane P prime. So in that way you can identify a series of ICRs. Fine. Now we go to different cases wherein it is possible to identify IAR and also ICR by visual inspection. There are three such cases I want to show here. Identifying IAR and ICR by visual inspection. And all these are for planar motion. Three cases. I am preparing myself for three cases here. Case 1. This is body M, this is reference frame F, ground. This is the angular velocity of M with respect to F. Very easy to identify where the ICR is lying and what the IAR is. We know by looking at this figure itself that VOF is 0. O does belong to the point body M, and thus ICR must be O, and the IAR is an axis passing through O and perpendicular to the plane of the screen. And then if you have any particle P belonging to the body, clearly VPF can be written simply as omega MF cross R P O. O is the ICR. Right? A very simple case, or rather the simplest of the three cases that I am going to show. Case 2. You have an RB undergoing planar motion with respect to this frame F. There are 2 points. At those 2 points, you know the direction of the velocity vector. You may or may not knowing the magnitude of the velocity vector, but you know the direction. Okay. So it is given A and B are fixed in the body M, and directions of VAF, VBF known. Also, VBF is not parallel to VAF is not parallel to VBF. This is also given. So this is not parallel to. The symbol I am using to show not parallel to. How do we find instantaneous axis of rotation and instantaneous center of rotation? In this case, what we need to do is you draw, first you go to point A and draw a line which is perpendicular to the velocity vector at A. and then you go to point B, and draw a line perpendicular to VBF. Let these points have to remove the heading because I have to locate the point where these two dashed lines are intersecting. They are intersecting here. I call this point as I. I is the instantaneous center of rotation of M with respect to F in the shown plane. And IAR will be a line perpendicular to this plane and passing through I. I passing through the ICR that I have located. And then, as usual, once you have found the instantaneous center of rotation, velocity of any point with respect to F can be written simply as omega mf cross RPI. That's the utility of instantaneous axis of rotation and instantaneous center of rotations. RPI. Where P is any point on the RV. M. That's the second case for us. Let's go to case 3. What does case 3 have to offer? We have this body M and F. Okay. In case 3, the given information is we know VAF, both magnitude and direction. Both mag and direction known. There is a point A, you know the magnitude and direction. So this is VAF. There is another point B which is known, both magnitude and direction. Okay, 2 points, velocity vectors known. Further, VAF is parallel to VBF. This is also a known information. Furthermore, it is known that RBA, to make a correction on the figure before I put the fourth known information, this is point B. Point B is here. It is known that the RBA vector is parallel to perpendicular to VAF and VBF, of course, because VAF and VBF are parallel. So when RBA is perpendicular to VAF, it is also going to be perpendicular to VBF. So I'll modify this also so that I can show the next step within the scope of my screen. So this is the situation: VAF, VBF known, magnitude as well as direction, VAF parallel to VBF, RBA perpendicular to both VAF and VBF. In this case, what happens? First, let's draw a line which is perpendicular to both VAF and VBF. Let's draw this line first. And then you connect the head of VAF vector with the head of VBF vector and extend this line and let it intersect the line that I earlier drew perpendicular to or along the RBA vector itself. Right? This is a line along the RBA vector, and this line I am drawing connecting the heads of the two vectors, and if it intersects here, this is our ICR. I denote it by point I. I is ICR, and as usual IAR is perpendicular to plane, the shown plane, and passing through I. This is the story. And then velocity of any particle F on the body can be written as omega mf cross r p I. This is the third case for us. In each of these cases, what I am saying, what I am suggesting as the step or the procedure to locate ICR is supported by mathematics. We can prove each one of these propositions. However, those proofs I am not including in this lecture. Now it turns out that the ICR of a body may not actually exist at a material point of the body. Even in this freehand sketches, the way I drew and tried to locate point I, we observed that, like in this case, we are able to find a point I, we are able to find ICR, but it seems like I is not lying on the body itself. Similar thing is happening here. I am able to locate I, but it seems to be falling outside the body. Indeed, that may happen for many bodies in planar motion, that I will not lie on a material point. However, I must lie on the massless extension of the body. Okay, so in cases where I is not lying on the material point of the body, we say that I is lying on the massless extension. What do I mean by that? Massless extension of the RB. what do we mean by massless extension of the RB? Massless extension, this particular phrase, is an imaginary extension of the body there lies no mass, there lies no mass. Clearly, that's why it is, since it is outside the body, there is no mass of the body, but we are saying it is an imaginary extension of the body, such that whatever the body does, I mean wherever the body goes, that massless extension goes with it. The massless extension goes with the body. So, the massless extension is an imaginary extension of the body. There lies no mass, but the massless extension is always connected to the body. It translates and rotates with the body. Wherever the body goes, the massless extension will go with it. Goes with it. If Q is a point on the massless extension of the body, M, by definition VQM will be 0 and AQM will also be 0. So in this way, Q is behaving just like any other point which Q behaves identically to a material point P, right? Because VPM is 0 and APM is also 0. P is a material point on the body. We know that VPM and APM must be 0. Similarly, if Q is a point on the massless extension, VQM and AQM will also be 0. So if ICR is found to be lying outside the material point, outside the material of the object or the RB, we say that ICR lies on the massless extension, which means that VICR with respect to M will always be 0 and A with respect to M will always be 0. Let me give an example of a situation, and that example will also help us understand what I really mean by massless extension. Suppose you have a ring we have a ring. Okay, radius r. Suppose it is executing a planar motion with respect to this frame F. These are the frame fixed axes. The motion is planar, and we know the velocity vector of this point here, VAF, is coming out of the plane here right now, and then I have a point B here which is having velocity VBF from left to right. Right? This is planar motion. VBF left to right, VAF, this is point A, VAF coming out of the plane of the screen. Where will the ICR be? So I draw a perpendicular line perpendicular to this VBF, and that will be somewhat like this, and I draw a line perpendicular to this velocity vector, which will be a line like this. I let them intersect at this point. This is where I will lie. This is ICR. ICR is lying at this point. Clearly, there is no material of the ring present at the location where I is. But then we will say that I is lying on the massless extension. Okay, such that VIF is 0, but VIM will also be 0, and AIM will also be 0. Now onwards, in fact, we will use the symbol. We will widen the scope of this symbol, and if I say that a point Q is an element of F, this will mean Q is a material point or a point, material point of M, or a point fixed on, or a point on the massless extension of M. So in that way we can say that for planar motion, whenever we are able to find the instantaneous center of rotation, point I, that will always be on M. Either a material point, I will either be a material point or it will be a on massless extension. Or a material point. Let's have a look at some cases of planar motion where we can quickly identify instantaneous center of rotation and instantaneous axis of rotation. Earlier we considered, in the beginning of this class, we considered a rolling cylinder on this surface of this frame F. For this observer, this point P1 is an element of M, so rolling without slipping. Rolling without slipping, P1 is ICR, instantaneous center of rotation. And a line passing through P1 and coming perpendicular, coming out of the plane, will be the instantaneous axis of rotation. Another case, we have two RBs. Let me call it RB1, which is a disc, and this is RB2, which is a rod. The disc is fixed to the ground at its center and it is free to rotate. Rod AD is pinned on the disc on one end, and on the other end it is connected to a sleeve which has the freedom to move upwards or downwards only, no horizontal motion possible. RB1 at this shown instant, RB1 has its instantaneous ICR is at B because VBF is 0, F is the ground frame. RB2, can we find locate the ICR of RB2 at this instant? So since A is hinged to the disc and the disc is rotating in a clockwise manner, we know that velocity of A with respect to F will be in horizontal direction. On the other hand, the velocity of D with respect to ground will be in the vertical direction. Now if we draw a line perpendicular to VDF and a line perpendicular to VAF, they meet at this point, and this will be the ICR of RB2.